Are you seeing this PPT? Is it
Yes,
appearing?
sir.
Is it appearing? Okay. So good evening, students. Today I am going to discussing about soil structures and clay mineralogy. So soil structures means it is a geometrical arrangement of soil particles in a soil mass. The behavior of soil mass depends upon the soil structure. So depending upon the type of soil structure, the soil may exhibits high permeability or low permeability, high settlement or low settlement, high shear strength or low shear strength. So all engineering properties depends upon soil structure. So the important soil structure that we have in geotechnical engineering is single grain structure, honeycomb structure, flocculated structure, dispersed structure, and composite structure. So depending upon the particle size and mode of formation, these are classified. So coming to composite structure, it is a structure formed in mixed soil. That means a clay, gravel, or sand, clay, sand, silt like that. In mixed soil, it will exhibit some structures. Let us see one by one. So single grain structures means while deposition of soil mass, it may take a loosest packing or it may take a densest packing. So it is present in soil like gravel and sand. The single grain structures appears only in gravel and sand. So while deposition of a soil mass, so it may take densest packing or lowest packing. So if particles are assumed as pairs, the loosest and densest packing are shown in figure. So loosest packing. So assuming that the soil particles are spheres, but truly it is not. It's not spheres. So in loosest condition, the soil may be like this, and densest condition, the soil in the second figure, the soil is in densest packing. So the wide ratio for the loosest state is 0.91. When soil particles are assumed as spheres and they are loosely packed, so maximum wide ratio is equal to 0.91. So when the soils are in densest packing, the minimum wide ratio is equal to 0.35. When the particles are assumed as perfect spheres, it is the assumptions only. So please keep in mind the soil particles are not truly sphericals. So maximum wide ratio is equal to 0.91, minimum wide ratio is equal to 0.35. So coming to engineering properties, loosest packing exhibits high permeability, low shear strength, high settlement, load carrying capacity. So when coming to densest packing, so the wide ratio less, permeability also less, density will be more, and strength of the soil also will be more, settlement will be less. Hence, we always see towards densest packing. That's why a compaction, a ground improvement technique is introduced in geotech engineering known as compaction. So compaction make the soil to pack densest state. So second one is honeycomb structure. Honeycomb structures means just like honeycomb. It consists of large voids. So large voids are bridges in between the soil particles. So such it look like a honeycomb. That's why it is called as honeycomb structure. So it is present in fine sands or silts. Fine sands or silts. This one gravel and sand. Please remember, single grain structure occurs in the case of gravel and sand. Honeycomb structure occurs in the case of fine sands or silts. So under vibration and shocks, and the structure collapses and large deformation takes place. So when the soil is subjected to high vibrations or any shock, what will happen? The attractive forces between the soil particles may destroyed, and they may accumulate within the voids, and it causes large deformation of the soil mass. Honeycomb structure. Next, flocculated structure. It occurs only in the case of clayey soils. So it occurs only in the case of clayey soils. Clay soil consists of positive charge on its edges and negative charges on its faces. So flocculated structure formed when there is a net attractive force between the particles. So when there is a attractive forces, positive charge attracts the negative charge. That's why when there is a net attractive force is more, flocculated structure is formed. So here we can see that edge to face orientation. Edge consists of positive charge, face consists of negative charge. So there is attraction between positive and negative. So edge to face orientation. So flat structure has a high shear strength because of attractive forces, low compressibility, high permeability. Because voids are there. That's why it exhibits high permeability and low compressibility. So low compressibility means voids are more. So because attractive forces, the bond between the particles will be more, and it exhibits the low compressibility under light loads. So dispersed structure, it occurs in the case of remolded clays. Remold means disturbed condition. When the soil is in disturbed condition or disturbed, then the soil is known as remolded soil. So dispersed structure occurs in the case of remolded soils. So face-to-face orientation takes place. Face-to-face, face negative charge. So here another clay also face negative charge. So negative charge, repulsive forces. So dispersed structure is formed when there is a net repulsive forces between the soil particles. So dispersed structure exhibits low shear strength, high compressibility, and low permeability. So depending upon the soil structure, it can exhibit the engineering properties of the soil mass. So when soil contains different types of particles, a compost structure is formed. That means mixture, clay gravel mixture, sand clay mixture, like that. So we have two types of structures in composite structure. One is coarse grain skeleton or contact structure. Coarse grain skeleton is a structure of soil which is present in composite soils containing both fine grain and coarse grain soil. When fine grain and coarse grain soils are mixed with together, then coarse grain skeleton or contact structure is formed. The coarse grain particle forms a skeleton-like structure, and voids between are filled by fine grain or clayey particles. So coarse grain structure forms a skeleton-like structure. Within that skeleton-like structure, it consists of voids. That voids are filled with fine-grained clay particles. Such type of structure is known as coarse grained skeleton or contact structure. Why it is called as contact structure means each particle has a contact. Each coarse grain particle has contact with each other. That's why it is called as contact structure. So another one is floating structure. So when fine grain soil is more than that of coarse grain soil, when clay particles is greater than coarse particles, floating structure is formed. Here there is no contact between the coarse grain soil. So it look like floating in soil. So the coarse grain soils are look like floating in soil. There is no contact between the coarse grain soil and coarse grain soil. So fine grain soil content is percentage is more when compared to coarse grain soil. So in such type of soils, floating structure is formed. So soil structure is over. Now coming to clay mineralogy. In gravel and sands, rock minerals like quartz, feldspar, mica, etc. are present. In clays, clay minerals are present. Important clay minerals are kyanite, illite, montmorillonite, and halazite. So kyanite, illite, montmorillonite, and halazite. These four are very important in geotechnical engineering. So coming to kyanite clay mineral, it consists of gibbsite sheet and silica sheet. Gibbsite sheet and silica sheet both are attached together with hydrogen bond. So two structural units. Here, gibbsite and silica sheet consists of one sheet, one structural unit. So another structural unit also there. These two structural units are connected by hydrogen bond. That's why this hydrogen bond very strong in nature. It does not allow the water to pass into the crystalline structure of the kyanite clay mineral. That's why it is not swelling in nature. So it completely prevents the entry of water into the lattice structure. So in kyanite clay mineral, silica sheet and gibbsite sheet. 1:1 mineral. It is 1:1 clay mineral. One silica sheet, one gibbsite sheet attached together. So two structures are connected by hydrogen bond. This hydrogen bond is fairly strong. It prevents the entry of water into the lattice structure of clay mineral. So it is called as stable mineral. So there no swelling, no shrinkage. It does not exhibit the soil consisting of kyanite clay mineral does not exhibit swelling and shrinkage. So it present predominantly in China clay. So kyanite clay present in China clay. So that clay is used to make dinner sets like pot, etc., etc. So coming to elite clay mineral. So it consists of a 2:1 clay mineral. Two silica sheets are sandwiched with one gibbsite sheet. So two silica sheets, two trapezium. So it is represented by trapezium, silica sheet. So rectangle is represented by gibbsite sheet. One gypsum sheet is attached with two silica sheets. Two structural units are separated by a potassium ions. This potassium ion is very weak when compared to hydrogen bond. That's why it allows some little water to enter into the lattice structure of the clay mineral. So potassium when compared to hydrogen bond, it is not that much as strong as a hydrogen bond. That's why it can allow a little bit of water to enter into the lattice structure. That's why it exhibits medium swelling and shrinkage. But elatic clay mineral does not exhibit swelling and shrinkage. So coming to montomonal clay mineral, it also similar to elatic mineral, but there is no connection between two structural units. So two structural units, there is no hydrogen bond, there is no potassium ions. So because of high net negative charge, it attracts the negatively charged water molecules in order to neutralize the ionic charge. It neutralizes the electronic charge. So due to attraction of water molecules, it exhibits large swelling when water is present. So during summer season, the water is dried out. So the soil which consists of more to more related clay mineral exhibits large swelling and large shrinkage. So highest percentage in present in bentonite followed by black cotton soil. So bentonite soil consists of more to so highest percentage is in bentonite soil. Next in black cotton soil. Black cotton also consists of Montmorillonite clay mineral. So halazite is similar to kaolinite clay mineral. Halazite is similar to kaolinite clay mineral. So it consists of gypsite sheet and silica sheet, and two structural units are separated by single layer of water layer. There is a big difference between kaolinite and halazite. Two structural units are separated by a single layer of water molecule. If water is dried out, halazite almost all approximately equals to kaolinite clay mineral. Next, diffuse double layer means diffuse double layer and adsorbed water. So the layer on the clay surface up to the limit of attraction due to electrical forces is known as diffuse double layer. So a clay surface consists of negative charge. This negative charge attracts the positively charged cations. This cation again attracts the negatively charged anions. Like there is a limit of attraction. So up to this limit of attraction, two thickness are there. One is clay particle thickness, another one is attractive because attractive forces, some cations and anions are there. So the clay particle, the thickness of clay particle along with this rigid layer is known as a diffused double layer. So the water held in the zone of diffused double layer is known as adsorbed water. So water which is held in diffuse double layer. Double layer means it consists of two layers. One is negatively charged clay particle, another one is rigidly held layer. So beyond the limit of attraction, attractive forces decreases. The water is in loose condition. They are not bonded by attractive forces. So there is a loosely held layer. So please ignore this loosely held layer. We can consider only clay particle surface and also rigid layer. The thickness of rigid layer as well as thickness of clay particle, these two together is known as diffused double layer. The water held in double layer, diffused double layer is known as adsorbed water. So present this adsorbed water present only on clay particles. Because of net electric charge present on the clay particles, water gets attracted and forms a bond. So adsorbed water imparts a blast with the clay. So elasticity, we can mold the soil into any shape, but in the case of clay soil, we cannot mold the soil into any shape. But in the case of clay soils, we can mold the soil into any shape. Because clay soil consists of negative charge on its surface, it attracts the negatively charged water molecules. So there is a bond develops between the clay particle and the water molecule. That's why we can make the soil into any shape. But the same thing is not possible in the case of sandy soils, because in sandy soil there is no negative charge, and also there is no interaction with the water with the sand particles. So because of this adsorbed water, clay exhibits plasticity. But when the clay is mixed with the kerosene, it does not make a bond with the kerosene, because kerosene is known as a non-polar liquid. Non-polar liquid. That means kerosene is electrically neutral, does not have negative charge, it does not have positive charge. So it is electrically neutral. That's why when soil is mixed with the kerosene, there is no bond between the it does not develop a bond between the clay particle because kerosene is electrically neutral. It is also called as a non-polar liquid. That's why in differential free swell index, while doing in laboratory, we will use one jar we will take water, in another jar we will take kerosene. So we will compare with the height of soil with the kerosene because in kerosene there is no interaction with the kerosene and water. That's why we can compare the height of soil with the height of soil in kerosene. So kerosene is used because it is a non-polar liquid, does not have any positive charge or negative charge. That's why it is called as a non-polar liquid, does not make any bond with the clay particle. So specific surface area, it is the total surface area of soil particles per unit weight or per unit volume. Total surface area of soil particles per unit weight or total surface area of soil particles per unit volume. So it is called as specific surface area. Higher the specific surface. So specific surface is inversely proportional to size of the soil. The size decreases, specific surface increases. So Mount Monad criminal has a largest specific area, surface area, about 800 meter square per gram. So please remember, highest specific area. So Mount Monad consists of highest specific area, about 800 meter square per gram. So this is about the soil structure and clay mineralogy. So now coming to index properties of soil mass. Soil properties are divided into two types. One is index properties, another one is engineering properties. So index properties again divided into two types: soil grain properties, soil aggregate properties. So soil grain properties we have size, shape, specific gravity and mineralogy. Soil aggregate properties we have unit weight, water content, relative density, Atterberg limits. So engineering properties it consists of permeability and seepage, consolidation, shear strength, bearing capacity, stability of slopes, like that. So what do you mean by index properties of soil? The properties which depend on individual soil grain and also soil formation is known as index properties. So these properties depends upon individual soil grain, ఒక్కొక్క soil grain. So take one single grain of solid grain, then we can have some properties. If you take whole soil mass as a whole, so total soil mass as a whole, then it will have some properties. These properties are known as index properties. So the properties which depend on individual soil grain and also soil formation are known as index properties. These properties are useful for classification and identification of soils. So index properties are useful for classification and identification of soils. It also gives a rough estimation of engineering behavior of soils. So it gives only rough estimation of engineering behavior of soils. Suppose density is the is known as index property. Density. So more the density, more will be the load carrying capacity. More the uh, d- uh, uh, more the density, less will be the permeability of the soil mass. So like that, the engineering property it indirectly correlates the engineering properties, but it cannot give the accurate value of the engineering property. It will indirectly correlate the engineering property. So it is highly compressible, it is low compressible, like that it can tell, but how much compressible it cannot give. So index properties are divided into two types. One is soil grain properties, second one is soil aggregate properties. So soil grain properties means the properties which are dependent on individual soil grain and are independent of and of soil formation. So it depends only on individual soil grain. So it does not depend upon manner of soil formation. These properties are known as properties of coarse grained soil. So soil grain properties also known as properties of coarse grained soils. The properties of these categories are size, shape, specific gravity, and mineralogical classification. So these properties are known as soil grain properties. So it depends upon only on particle, individual particle. The properties based on individual soil particle, that properties are known as soil grain properties. Example: shape, size, specific gravity, and mineralogical classification. Soil aggregate property means soil aggregate property depends on soil mass as a whole. It represents the collective behavior of the soil mass. Collective behavior of the soil mass. The properties in these categories are water content, fuel density, relative density, and consistency limits or Atterberg limits. So here, if you take a class, individual student, based on individual student, we can have some idea. That is known as a soil grain. So the collective behavior of a total students in the class is known as soil aggregate. You can imagine like that. Individual student, soil grain, total collective behavior of the students in the class, soil aggregate. So coming to engineering properties, the properties of soil which are utilized by civil engineering to design and maintain stability of civil engineering structures are called as engineering properties. So these properties included are permeability and seepage, consolidation, shear strength, bearing capacity, etc. So the properties which are utilized by civil engineer to design and maintain the stability of structure is known as engineering properties of the soil mass. So example for engineering properties are permeability and seepage, consolidation, shear strength, bearing capacity, etc. So coming to one by one, soil grain properties, shape. So based on shape, soil grains are classified into three types: bulky grains, flaky grains, elongated grains, or needle-shaped grains. Bulky grains means the length, width, and the thickness of a soil particle is of same order of magnitude. That means length, width, thickness, both they are same, approximately equal. Such type of grains are known as bulky grains. So they are divided into three types: angular, subangular, well-rounded. So bulky grains means length, width, and thickness of soil particle are approximately equal in magnitude. So bulky particles are again divided as angular, subangular, well-rounded. So angular, the particles with high value of angularity is known as angular soil particle. The particle with the sharp edges are known as angular particles. So angular particles resist the displacement but more tendency for fracturing. So when load is applied to soil mass, it can take the loads. It can resist the settlement, but they will tend to fracture under the action of the loads. So angular particles. So well-rounded. The particles with low angularity don't crush easily under loads, but have low resistance to displacement. There will be lateral deformation or there will be vertical deformation. There will be deformation of the soil particles we can observe. But the particles with low angularity, they can crush, they don't crush under easily under load. That is the difference between angular and well-rounded. Angular particles crushes easily under loads, but well-rounded particles does not crush easily under loads. Angular particles resist the displacement, but well-rounded particle does not resist the displacement. So bulky grains can support any loads in static condition, but when vibration takes place, large deformation occurs. So next, second category is flaky grains. Flaky grains means the thickness is negligible when compared to other dimensions of the grains. The grains which have very negligible thickness when compared to other dimensions are known as flaky grains. These grains are crushed easily under loads. Next, the last one is elongated or needle shaped grains. So length is more when compared to thickness and width. So when compared to thickness and width, the length is considerable. Length is significant. So length is more when compared to thickness and width. So these grains are crushed easily under loads and not stable and stable subject to vibration. So they can easily crushed under the loads, but they are stable when subjected to vibration. So coming to specific gravity, it is the ratio of weight of soil to the weight of equal volume of water. It is determined by the following methods: density bottle method, measuring flask method, and 5 km method. Density bottle method is suitable for fine grain soils. Measuring flask method is suitable for medium grain soils. 5 km method is suitable for all types of soils. So the neck is a large size, so it can be used for fine grain soil. It can also be used for coarse grain soil. That's why 5 km method can be used for all types of soils. So this is the specific gravity determination. So generally specific gravity expressed at 27 degrees or 4 degrees centigrade. So please remember specific gravity is expressed at 27 degrees centigrade or 4 degrees centigrade. Suppose if specific gravity is taken at 30 degrees centigrade, we need to convert it to 27 degrees or 4 degrees centigrade. So for conversion, we have one formula specific gravity at 27 degrees centigrade or 4 degrees centigrade is equal to specific gravity at room temperature into specific gravity at 30 degrees room temperature divided by specific gravity at standard temperature. Standard temperature means it may be 27 degrees or 4 degrees centigrade. The specific gravity at 27 degrees centigrade or 4 degrees centigrade is equal to specific gravity at room temperature into specific gravity of water at 30 degrees next divided by specific gravity of water at 27 degrees centigrade or 4 degrees centigrade. So G 30 degrees means specific gravity of soil. Specific gravity of soil. Specific gravity 30 degrees means specific gravity of water at 30 degrees centigrade. Specific gravity of water at 27 degrees centigrade or 4 degrees centigrade. So in soil grain properties, the second property is size. The size is determined by using sieve analysis or sedimentation analysis. So sieve analysis is done for coarse grained soil. Coarse grained soil means when percentage is more than 50% retained on 75 micron ISU. If more than 50% of soil retains on 75 micron ISU, then the soil is known as coarse grained soil. The C1 is done for coarse grained soil only. Next, sedimentation analysis. When more than 50% passes through 75 micron ISU, that means more than 50% of soil has a size less than 75 micron ISU. So sedimentation analysis is done for fine grained soil. So C1 is done for coarse grained soil. Sedimentation is done for fine grained soil. So dry sieve in sieve analysis again we have two types of sieve analysis: dry sieve analysis, wet sieve analysis. In sedimentary analysis we have two methods: pipette analysis, hydrometer analysis. So dry sieve analysis we don't use water. In wet sieve analysis we will use water. In pipette analysis and hydrometer analysis, both the methods works under the Stokes law. So both the methods use in both the methods the mechanism is Stokes law. So particle size distribution. So grain size distribution curve is obtained by sieve analysis and sedimentation analysis. So dry sieve analysis is used for cohesionless soils only. Dry sieve analysis is used for cohesionless soils. Wet sieve analysis is used for cohesive soils or soil containing fines. Versive analysis used for cohesive soils or soil containing fines. So sieve analysis is connected for coarse grained soils. Sedimentary analysis is for fine grained soils. So sedimentary analysis is based on Stokes law. So Stokes law means Stokes law says that in an infinite amount of water, if a single sphere is allowed to fall freely, the terminal velocity of sphere depends upon shape, size, and weight of the sphere. So Stokes law says that in an infinite depth of water, if a single sphere is allowed to fall freely, its velocity is increased first under the influence of gravity, but a drag force comes into action and reduces the velocity. So after adjustment of the sphere attains a steady state velocity, which is known as constant velocity or terminal velocity. So Stokes' law says that in an infinite depth of water, if a single sphere is allowed to fall freely, its velocity is increased first under the influence of gravity, but a drag force comes into picture. This drag force reduces the velocity. So initially velocity is more, then because of this drag force, velocity gradually reduces. After the adjustment of the sphere attains a steady state velocity, a constant velocity. This constant velocity is known as terminal velocity. So Stokes law terminal velocity is given by terminal velocity is equal to 1 by 18 into d square into gamma s minus gamma w divided by mu. So our terminal velocity is equal to g by 18 into s minus 1 into d square by viscosity. So d equal to diameter of particle, Gamma is equal to unit weight of particle, mu equal to dynamic viscosity of water, V equal to kinematic viscosity of water, which is given by dynamic viscosity divided by density. Kinematic viscosity of water equal to dynamic viscosity divided by density. So approximate version of Stokes law. So after substituting this G value, viscosity of water, then we will get V equal to approximately 900 into d square, where d is known as diameter of the particle in mm. So velocity is in millimeters per second. So there is a gate question is there. For a particle of diameter 75 microns, what will be the terminal velocity? So particle diameter is given 75 microns. So terminal velocity is equal to 900 into d square. So 75 into 10 power minus 3 millimeters. So Vs is equal to 900 into 75 minus 3 whole square. Finally, we will get 5 millimeters per second. So, even though Stokes' law is popular, it has some limitations. So, Stokes' law considers that the velocity of free fall of a single sphere in suspension of infinite depth, where as size analysis, a glass of limited depth is used. So, Stokes' law says that when a sphere is allowed in a infinite depth of fluid medium, infinite depth, but in sedimentation analysis, we will use a glass jar of limited depth. So glass jar means it has some limited depth, but it's assumed that it is a infinite depth. That's why it has some limitations. A Stokes law is based on assumption that the falling particle is a spherical shape, but in actual practice, is soil particle is not never truly spherical. So it is assumed that it is a spherical sphere, but soil particle is not truly spherical. They are usually flaky or needle shaped. That is also one more limitation. Next, sedimentation analysis can't be used for soil particles larger than 0.2 millimeters because turbulent condition develops and Stokes law is not applicable. The sedimentation analysis can't be used for small particles larger than 0.2 mm. So when these particles are placed in water, turbulent flow conditions develops. So Stokes law is not valid for turbulent flow conditions. So sedimentation is not applicable for particles less than 0.2 microns, as Brownian motion movement takes place and particle does not settle. So Brownian motion means the particle moves in upward direction, again it moves in downward direction, again it moves to upward direction. It never settles. That's why we cannot use the Stokes law here also. So Stokes law is valid only if the size of the particle is between 0.2 mm and 0.2 microns. So please remember, this is one more question. Stokes law is valid only if the size of the particle is between 0.2 mm and 0.2 microns. 1 micron equal to 1 by 1000 millimeters, or 1000 millimeter, 1 millimeter is equal to 1000 microns. So in sedimentation analysis, we need to keep to some points in mind. So pipette method is a sedimentation method used in laboratory. It is an accurate method. So pipette method and hydromet method, two methods are used for sedimentation analysis. When compared to hydrometer method, pipette method is an accurate method. Next, dispersion solution containing 33 grams of sodium hexametaphosphate and 7 grams of sodium carbonate in distilled water is to make 1 liter of solution. So, in order to make 1 liter of distilled solution, 33 grams of sodium hexametaphosphate and also 7 grams of sodium carbonate in distilled water is added, because these two agents act as a dispersing agents. That means it will increase the repulsive forces between the soil particles. So the particle attached to the coarse grained soil, the fine grained soil attached to the coarse grained soil may be separated because of this dispersing agent. What is the dispersing agent? 33 grams of, please remember along with the weight, 33 grams of the sodium hexametaphosphate and 7 grams of sodium carbonate in distilled water. So the process of removal of organic matter and calcium compound is known as pre-treatment. So before using for sedimentation analysis, the organic matter present in soil and also calcium compound present in the soil will be removed. So such type of procedure is known as pre-treatment. The hydroid method of sedimentation analysis differs from pipette analysis in the method of taking observations only. So both the methods are same. Both the methods are same. Both the methods utilize the Stokes law. But the hydromet method of sedimentation analysis differs from pipette analysis in the method of taking observations only. So in hydromet analysis, so we have some corrections. Some corrections may negative, some corrections may be positive. So which is negative, which is positive, you should remember. Meniscus correction is always positive. So always you need to add plus. So meniscus correction CM is always positive. Dispersing agent correction CD is always negative. So dispersing agent correction CD is always negative because it increases the density of the water. So it increases the density of the water. That's why we need to take consider it as a negative. So temperature correction is positive when greater than 27 degrees centigrade and negative when less than 27 degrees centigrade. So temperature correction is positive when greater than 27 degrees centigrade and negative when less than 27 degrees centigrade. The hydrometer reading increases on the downward direction towards the hydrometric bulb. So hydrometer reading increases. So towards the in downward direction towards the hydrometer bulb. So that means from top to center of the bulb, the hydrometer reading increases. So reading is taken corresponding to the upper level of the meniscus. So reading is taken corresponding to the upper level of the meniscus. So please remember here, meniscus correction always positive, dispersing agent correction is CD is always a negative, temperature correction is positive when greater than 27 degrees centigrade and negative when less than 27 degrees centigrade. So these are the particle size distribution curve. So particle size distribution curve means the curve which is plotted between cumulative percentage finer taking on y-axis and the particle sizes in in logarithm scale. So we are using semi-logarithm scale. So the x-axis is taken in logarithm scale, y-axis is taken in normal scale. So y-axis consists of cumulative percentage finer and x-axis consists of particle size in So from the graph, we can see that the curve which is situated close to x-axis is known as fine grained soil. The curve which is situated very far away from x-axis, y-axis is known as coarse grained soil. The curve which is steep S curve. The curve which is steep S curve is known as uniformly graded soil. The soil with flat S curve is known as well graded soil. The curve which is having some hump are known as gap graded soil. So we have five types of soils. Fine grained soils which are situated very near to y-axis. Coarse grained soil which is some very far away from the y-axis. So there is a steep S curve which is known as uniformly graded soil. So there is a flat S curve which is known as well graded soil. The curve with hump are known as gap graded soil. So uniformly graded soil means all particle sizes are equal. Well graded soil means all particle sizes are equally proportionate. That means the soil consists of equal proportions of fine grained particles, coarse grained particles, or medium sized particles. So gap grade soil means some intermediate particle size ranges particles are missing. Some intermediate particle sizes are missing. Such type of soil is known as gap graded soil. So the particle size distribution gives the rough idea about the particle size in and rough idea about the soil and also gradation of the soil. So which type of soil it is, it can give at the same time what is the gradation of the soil also it can give the information. Particle size distribution curve. So the curve drawn between cumulative percentage final and particle size taking in logarithm scale. A give idea about the type of soil and gradation of soil. A curve situated higher up on left hand side of the graph is known as fine grained soil. Example flat clay. A curve situated far away from the y-axis is known as coarse grained soil. A curve with hump represents gap grade soil or skip grade soil. A flat curve, a flat S curve represents a soil which contains the particles at different sizes in good proportion. Such soils are called as well-graded soil. Example: glacial deposit soils. Example: different drifts, till, moraines, drumlins. These are example for well-graded soil. A steep S curve indicates the soil containing the particles are almost the same size. So steep S curve, you can see in the figure. Third one, steep S curve. So it consists of uniformly graded soil. So wind deposit soils, alien deposits are example for uniformly graded soil. So all particle sizes are in equal proportions. So alien deposit soils such as dunes, Louis are termed as uniformly graded soil. So here we have three terms. One is effective size or effective diameter, coefficient of curvature, coefficient of uniformity. So effective size means it is expressed at D10. D suffix 10. It is expressed in mm. It means that only 10% of particles are finer than this size. So if you take 1 kg soil mass, 10% of that soil only passes through D10 size, 10 D10 size. So only 10% of particles are finer than this size. The coefficient of uniformity Cu is equal to D60 by D10. So it is a measure of particle size range. It always greater than or equal to 1. A soil is called uniformly graded if Cu lies between 1 and 2. So for a well-graded gravel, Cu must be greater than 4. Whereas for a well-graded sand, Cu must be greater than 6. So if Cu is greater than 6, it is called as sand. If Cu is greater than 4, it is called as gravel. So coefficient of curvature is equal to D30 square divided by D60 into D10. So it represents the shape of particle size curve. So for well-graded soil, Cc lies between 1 and 3. If Cc value is in between 1 and 3, it is called as well-graded soil. For uniformly graded soil, Cc is equal to approximately equal. For uniformly graded soil, D60 equal to D10 equal to D30. So numerator and denominator both are cancelled with each other. Cc value is equal to 1. So use of particle size distribution curve. The particle size distribution curve gives idea of a idea and type of soil and gradation of soil. It is used for classification of coarse grained soil. It gives a rough idea about permeability of soil. It is required for design of filters. It provides information for rough estimation of shear strength of soil. Example: a well-graded soil has high shear strength, low permeability, high density, and when compared to uniformly graded compressibility of soil. So it provides information. That means particle size distribution curve provides information for rough estimation of shear strength of the soil. Suppose from particle size distribution curve we can identify that well-graded soil we can identify, and also poorly graded soil, uniform graded soil also we can identify. So when comparison is taking place between well-graded and uniformly graded soil, we have that well-graded soil has high shear strength, low permeability, high density compared to uniformly graded soil. Compressed soil can be judged from particle size distribution curve. A uniformly graded soil is more compressible than well-graded soil. A uniformly graded soil is more compressible than well-graded soil because in uniformly graded soil, voids are not filled by fine particles. So voids are empty. When load is applied, the soil particles may adjust within the voids so that compressibility is more. But in the case of well-graded soil, the voids formed by coarse grained soil is filled by fine grained particles. That's why compressibility is less. So soil aggregate properties. So till now we discussed about soil grain properties. So now I am going to discuss soil aggregate properties. In soil aggregate properties we have relative density or density index. So this property is most important for coarse grain soils only. It indicates the relative compactness of the soil mass. That means the soil is a dense, loose or medium dense, like that it can give the information. So relative density is equal to E max minus E divided by E max minus E minimum. E max is equal to maximum void ratio in loosest condition. E minimum is equal to minimum void ratio in densest condition. E is equal to natural void ratio. So this relative density ranges in between 0 to 100. So here relative density is expressed in terms of void ratio E max minus E by E max minus E minimum. It can be expressed in terms of unit weight also. So gamma D is known as dry unit weight in loosest condition. Gamma D minimum means dry unit weight in loosest condition. Gamma D maximum means dry unit weight in the densest condition. Gamma D equal to in situ dry unit weight at void ratio E. So next soil aggregate property is water content. So water content equal to weight of, it is a ratio of weight of water to the weight of dry soil into 100. So this water content is determined by overlaying method, calcium carbonate method, alcoholic method, pyranometer method, and radiation method. So in woven dyeing method, it is the most accurate method among all. So it is the more, please remember, most accurate method is woven dyeing method. Temperature to be maintained in the oven is 105 degrees to 110 degrees centigrade for 24 hours. Please remember 105 degrees to 110 degrees is maintained for 24 hours. For highly organic soils, a low temperature of about 60 degrees is preferable. If gypsum is present, temperature should not be more than 80 degrees centigrade. But for a long time, you need to maintain temperature 8 degrees for a long time if gypsum is present in the soil mass. If soil mass consists of highly organic soils, then we need to maintain low temperature of 60 degrees. So 60 degrees is preferable. So for normal soil, the temperature to be maintained in the oven is 105 degrees to 110 degrees centigrade. Next, third method is calcium carbonate method, also called as rapid moisture meter method. So very important one more question. It is known as quickest method. So we have so many methods. So calcium carbonate method is called as quickest method among all. It takes only 10 minutes to determine the moisture content. So it is useful for field compaction. So it is a portable equipment which can be conveniently used in the field as well as portable. That means it can be it can be taken along with us from one place to another place. But means that means for transportation is easy. It is a handy equipment. So the amount of acetylene gas, the amount of acetylene gas released indicates the approximately the water content. So more the water content, more will be the release of acetylene gas. If the less the water content, less will be the release of acetylene gas. So based on the pressure applied by acetylene gas is taken as reference to tell the moisture content. So when acetylene gas is produced, it exerts some pressure on the top of the vessel. So depending upon the pressure exerted by the acetylene gas, we can give the amount of moisture content. So radiation method. It is suitable to determine the water content of soil in the in situ condition in a borehole at required depth. So in situ condition. So till now I discussed that it is in a laboratory, but it is in a practical. If it is a practical method, we need to go for radiation method. Radiation method is a practical method. It is suitable to determine the water content of soil in the in situ condition in a borehole at a required depth. So next torsion burn method is for quick determination of water content of soil in the laboratory. So for quick determination of water content of soil in the laboratory, we need to go for torsion balance method. So alcoholic method, there is no, so in this method there is no control on temperature. Just the soil is mixed with alcohol, then it is ignited. So when during ignition, what will happen? It will evaporate all the moisture. So after evaporation, the only the soil is left. So that's why we can find out the weight of the soil before drying with alcohol and weight of the soil after burning with alcohol. So there is no control on the temperature. This method is not suitable for organic soil and soil containing gypsum. The sand bath method, it is a field method. It gives high temperature which may break the crystalline structure of the soil mass. So sand bath method, sand is used. Sand is heated up to great temperature. Then over this heated sand, a container is placed. Container consisting of water, container consisting of soil is placed. So this method is not suitable for organic soil and soil containing gypsum because of production of high heat. This method is not suitable for soil containing gypsum. So next method is pyrometer method. So pyrometer method also used to determine the water content as well as specific gravity. So the method used to determine the water content and specific gravity is pyrometer method. So pyrometer method is used to determine both the water content as well as specific gravity. So pyrometer method is suitable for coarse grained soils only here to determine the water content. To determine the specific gravity, it is suitable for all types of soils. To determine the specific gravity of the soil, phytometer method is suitable for all types of soils. For to determine the water content, phytometer method is suitable only for coarse grained soil. That's why you need to very careful while dealing with objective questions. If it is water content, suitable for coarse grained soils only. If it is specific gravity, phytometer method is suitable for all types of soils. So water content is determined when specific to soil is known. So we can have the equation at the bottom of this slide. W2 minus W1 by W3 minus W4 into G minus 1 by G minus 1. So third soil aggregate property is in situ density. It is the ratio of weight of the soil to the volume of the soil mass. So in situ density means it is the ratio of weight of soil mass to the volume of soil mass. So to determine the in situ density, we have five methods. One is core cutter method, sand replacement method, rubber balloon method, water displacement method, and radiation method. So core cutter method, it is used only for soft soils. Sand replacement method is used for all types of soils, provided soil should be soft to cut by the digging tool. So water displacement method, it is used for cohesive soils where it is possible to make a lump of soil. So that means it is suitable only for cohesive soil. For cohesive soils, we can make a lump of soil. So rubber balloon method. So it is used for all types of soils, but it is very difficult to fit the rubber balloon accurately in a pit. That's why it is called as an approximate method. So it is used for all types of soils, but it is not so accurate as it is difficult to fit the balloon exactly in an irregular hole. That's why it will give a uh, wrong volume of the hole because a hole is irregular. The rubber balloon will not fit accurately, so that way it cannot give accurate volume of the hole. So radiation method, it is used for rocky soils or hard soils. Next, limits of consistency or outer bug limits. So depending upon the water content, the soil behavior may be changed. So depending upon the water content, soil acts as a liquid. As the water content decreases, the soil comes into plastic state. So further the water content decreases again. What will happen? The soil comes to semi-solid state. So if again the water content is reduced, the soil comes in solid state. So depending upon the water content, the state of soil changes. So the water content at which the soil changes from liquid state to plastic state is known as liquid limit. The water content at which the soil changes from plastic state to semi-solid state is known as plastic limit. The water content at which the soil changes from semi-solid state to solid state is known as shrinkage limit. So liquid state, the soil is like a soup. In plastic state, the soil is like soft butter. In semi-solid state, the soil is just like a curd. In a solid state, the soil is just like a candy. So automatic limits are the water contents at which the soil passes from one state to the next state. So depending upon the water content, the soil may be in liquid state, the soil may be in plastic state, the soil may be in semi-solid state, the soil may be in solid state. So liquid limit, it is the minimum water content at which the soil is still in the liquid state but has a small shear strength against flowing. So it is the minimum water content at which a part of a soil cut by a groove of standard dimensions will flow together for a distance of 12 mm under an impact of 25 number of blows in the device. So under an impact of 25 number of blows, the gap should be touched. So flow curve. So flow curve gives an idea of shear strength variation with water content of the soil. The soil passing through 425 micron SCV is used for the test. The drop of the cup on the hard base is 1 centimeters. The shear strength of the soil at liquid limit. Please remember the shear strength of the soil at liquid limit is about 2.7 kilonewton per meter square. So flow curve means the curve drawn between number of blows and water content. So flow index is equal to, it is the numerical difference between water content to the logarithm of number of blows, ratio of number of blows, w1 minus w2 by log 10 n2 by n1. So if is known as flow index. It shows the, it indicates the slope of the flow curve. So plastic limit. It is the minimum water content at which the soil can be rolled into a thread of 3 mm in diameter without crumbling. It is determined by plastic limit test or thread test. So it is the minimum water content at which the soil can be rolled into a thread of 3 mm in diameter without crumbling. It is determined by plastic limit test or thread test. Shrinkage limit means it is the moisture content after which further loss of moisture does not cause a decrease in the volume of the soil mass. That means if you see this figure, as from right hand side to left hand side, as the water content decreases, what will happen? There on a y-axis there is a volume. So as the water content decreases, the straight line gradually decreases up to solid state shrinkage limit. So up to shrinkage limit, there is a decrease in volume of the soil mass. After shrinkage limit, the volume remains constant. That means if you evaporate the water, what will happen? The volume of soil decreases. But at shrinkage limit, if you further evaporate the water, the soil will not change its volume. The volume remains constant. So at shrinkage limit, it is the moisture content after which further loss of moisture does not cause a decrease in the volume of the soil mass. That means as the loss of moisture causes, what will happen? Volume also decreases. But after reaching the shrinkage limit, if you evaporate the water, there is a loss of moisture. Volume does not decrease. The volume becomes constant beyond shrinkage limit. So shrinkage limit is the lowest water content at which a soil can still be completely saturated. So shrinkage limit is the lowest water content at which the soil can be still completely saturated. Please remember, at shrinkage limit, the soil is still fully saturated condition. So you can see here, as the water first figure 1, as the water evaporated, what will happen? Gradually the volume also decreases. After reaching shrinkage limit, if water is dried out, there is no decrease in volume. The volume remains constant. So at shrinkage limit, the volume remains constant. So we have the shrinkage limit. We have formulas. So please remember, water content is equal to E by G, because SE equal to WG. We have one relationship, but at shrinkage limit, degree of saturation is equal to 1. That's why water content shrinkage limit equal to E by G. So here one get problem is there. A clay sample has y dash of 0.50 in the dry condition. The grain specific dot has been determined as 2.72. So what is the shrinkage limit of this clay? So shrinkage limit is equal to, see here, W equal to V by G. So WS equal to shrinkage, water content shrinkage limit equal to E by G. So we will get shrinkage limit equal to 18.4%. So we have some numerical index also, plasticity index, shrinkage index. So plastic index means It is a numerical difference between liquid limit and plastic limit. So it is relatively more for plastic clay cells. So plasticity index is more for clay cells. So more the plasticity index, what is the meaning? It indicates more clay particles present in the soil mass. So plastic index is the numerical difference between liquid limit and plastic limit. So depending upon the plasticity of the soil mass, so the soil can be classified as non-plastic if IP equal to 0, low plastic if IP equal less than 7, medium plastic if the IP is in between 7 to 17, highly plastic it is greater than 17. So shrinkage index is equal to, it is a numerical difference between plastic limit and shrinkage limit. So toughness index is equal to, it is a ratio of plasticity index to the flow index. So significance is larger the value, better the strength of the soil at its plastic limit. So if toughness index value is more, it indicates the strength of the soil is more. So liquidity index IL is equal to W minus WP by IP. W means water, natural water content. W suffix P is known as plastic limit. IP is known as plasticity index. So consistency index or relative consistency. IC is equal to liquid limit minus natural water content to the plasticity index. It is a ratio of numerical difference between liquid limit and natural water content to the plasticity index. So it is useful in the study of field behavior of the saturated fine grained soil. It can be greater than or less than 1. If IC is equal to 1, soil is at plastic limit. If IC is equal to 0, soil is at liquid limit. If IC is greater than 1, the soil is in semi-solid state and stiff. If IC is in negative, it indicates that the natural water content is greater than liquid limit and hence behaves like a liquid. So if IC is negative, don't show the negative value. We should report it as a 0. So please remember, if IC is negative, we should report it as a 0. So the liquidity index is also known as water plasticity ratio. So the liquidity index is IC plus IL is equal to 1 or 100%. So in fractions equal to 1, in percentage is 100%. So the next soil aggregate property is activity. It is a ratio of plasticity index to the percentage of clay fraction. So it is a measure of water holding capacity of the clay soil. So activity is equal to plasticity index divided by percentage of clay fraction. The swelling and shrinkage characteristics are represented by a number called activity number. The soil containing the clay mineral mountain have very high activity. Activity is greater than 4. If activity is less than 0.75, inactive. If activity is equal in between 0.75 to 1.25, normal. If A is greater than 1.25, it is active. So for a soil of specific origin, the activity is constant. So remolding causes a loss of strength in cohesive soils. So generally cohesive soils, after adjustment, it consists of a flagellated structure. When the soil is disturbed, what will happen? These flagellated structure is disturbed and uh, dispersed structure will it takes place. That is known as remolding. So because of dispersed structure, loss of strength may occurs. So remodeling causes loss of strength in cohesive soils. So thixotrophy means the phenomenon of regaining of lost strength with passage of time with no change in water content is known as thixotrophy. So when the soil is undisturbed condition, it possesses some structure and also strength. When the soil is disturbed, what will happen? The structure may be disturbed and also it may lose some strength. So if you left the soil as it is for some time, what will happen? At the passage of time, it again regains its strength, which is known as thixotrophy. The thixotrophy means the soil loses its strength due to disturbance. But after disturbance, if the soil is left as it is, as a passage of time, again the soil gains its strength. That property is known as thixotrophy. So consistency means it is the resistance offered by soil against deformation. It varies with the water content. It is a resistance. That means soil tries to deformation, but it offers some resistance. So that is known as consistency. It depends upon water content. More water content, less consistency. Less water content, more consistency. So plasticity means it is a property which allows it to be deformed without rupture. That means it is the ability of soil to deform. So it is the, I think both are opposite words. Consistency means it is the deformation. It is the resistance offered by the soil against deformation. Plasticity means it is the ability of soil to deform. Plasticity is the ability of soil to deform. Consistency is the resistance offered by soil against deformation. Both depends upon water content. So coming to some gate problems. So in a grain size analysis of soil, the grain size values and corresponding percentage are obtained as below. So here we need to find out the Cu value and Cc value. So Cu value equal to D60 by D10. Cc value equal to D30 square by D60 into D10. Here D60, that means percentage final. See here, percentage final 60, grain size equal to 1. So D60, grain size equal to 1. For D10, see the percentage final. For D10, 0.075. 0.075 is the value there. So there is a correction here. Instead of 0.0075, I have taken 0.075. So D10 equal to 0.075. So Cu is equal to D60 by D10, 13.33. So Cc equal to D30 square by D60 into D10, D30. So see the percentage final here, D30. So exactly opposite to 30. What is the size? 0.3. So 0.3 whole square, D60 1, D10 0.075. The Cc value equal to 1.2. The Cu value greater than 6, Cc value is 1.2. If Cc value is in between 1 and 3, well graded, Cu is greater than 6, it is called as sand. So well graded sand. The soil is classified as well graded sand. So second one is, for a soil, the coefficient of uniformity is Cu is equal to 6. Cc is equal to 1.5. Effective size of the soil is 0.001 mm. So effective size means D10. So we need to find out the D30 size. So we in the problem we have that Cu is equal to 6, Cc is equal to 1.5, D10 is equal to 0.001 mm. So Cu is equal to D60 by D10. So D60 is equal to 0.006. Cc is equal to D30 square by D10 into D60. So instead of D60, I have taken 0.006. Now D30 square equal to 1.5 into 0.001. That means effective size into 0.006. So D30 size equal to 0.003 mm. So next problem, the coefficient of curvature and coefficient of uniformity is 1 and 4 respectively. Find the ratio of D30 by D10. So we have Cu is equal to 4, Cc is equal to 1.0, Cu equal to D60 by D10. So Cc is equal to D30 square by D60 into D10. So Cc we have 1. So D30 square by D60, instead of D60 I have taken 4 into D10. So 4 into D10 into D10. What will happen? 1 is equal to D30 square by 4 D10 square. So I am taking D30 square by D10 square. So is equal to 4. So square, if you if it goes away from the it goes opposite side, D30 by D10 is equal to square root of 4, 2. So D30 by D10 is equal to 2.0. So this problem is regarding density index. So here the dry unit weight of sandy soil in loosest condition is 13.34 kilonewton per meter cube and the densest state is 21.19 kilonewton per meter cube. So we need to find out the density index of sand when the soil has porosity of 33%. So grain specific gravity equal to 2.68. So this problem can be done in two ways. One is by taking into consideration of dry unit weight. Second one is by taking consideration of void ratio. So if void ratio ID equal E max minus E by E max minus E minimum. If it is density ID equal to gamma D max divided by gamma D into gamma D minus gamma D minimum by gamma D max minus gamma D minimum. So gamma D max already given, gamma D minimum also given. So porosity we know that. So E can be obtained by porosity equation 0.492. So dye unit weight at natural condition is equal to G gamma W by 1 plus C. So G equal to 2.68 into gamma W taking 10, 1 plus E equal to 0.492. So natural condition gamma D equal to 17.98 kilojoule per meter cube. We know that gamma D max and gamma D minimum. Substituting these values in ID, we will get approximately 69.69%. So the same problem we can try in another equation. ID equal E maximum minus E by E maximum minus E minimum. So we know that gamma D maximum, gamma D minimum, and also E 0.492. So gamma D maximum is equal to G gamma W by 1 plus E minimum. Where minimum mind ratio is there, we will get maximum dye density. So gamma D maximum equal to G gamma W by 1 plus E minimum. So E minimum is equal to G gamma W by gamma D max minus 1. So if we substitute in the equation the values, we will get 0.264 E minimum. So similarly, E maximum is equal to 1.008. So E maximum we know that E maximum and E minimum and also E value. So the consistency, the relative density is equal to here also 69%. So we can use this equation or that equation. So whichever is convenient, we can use that equation. So problems on index properties. So in a liquid limit test, the water content for a 10 and 100 number of blows is 40% and 10% respectively. The flow index of soil is dash. So flow index is equal to difference in water content divided by log n1 by n2. So 40 minus 10 divided by log 100 by 10. We will get the flow index value. So a soil sample has a soil sample has shrinkage limit. At shrinkage limit, water content is 10%. The specific of particle also 10%. So we need to find out the porosity. So we know that water content equal to 10%, G equal to 2.7. At shrinkage limit, degree of saturation equal to 100%. So SE equal to W into G, E equal to W into G, E equal to 0.1 into 2.7, 0.27. So if you for finding out the porosity, N is equal to E by 1 plus C. By substituting E by 1 plus C, we will get the porosity of the soil sample. Then the liquid limit and plastic limit of soil is 100% and 25% respectively. In hydromet analysis, it has been found that the soil consists of 50% of clay fraction. Find the activity of the soil and make a comment. So activity is equal to, it is the ratio of plasticity index to the percentage of clay fraction. So plastic index is equal to liquid limit minus plastic limit divided by percentage of clay fraction. So liquid limit 100 minus plastic limit 25 divided by percentage clay fraction 50. Activity is equal to 1.5. If activity is equal to 1.5, the soil is treated as active soil. So next one is a soil has a liquid limit of 25%, flow index 12.5%. If plastic limit of soil is 15%, determine the plasticity index and toughness index. So liquid limit is 25%, plastic limit is 15%. Plasticity index is equal to liquid limit minus plastic limit. So 25 minus 15, 10%. So IT equal to toughness index, the ratio of IP by IT. IP is equal to plasticity index 10 divided by toughness index equal to so divided by flow index is equal to 12.5. So toughness index is equal to, it is the ratio of plasticity index to the flow index. Plasticity index 10, flow index equal to 12.5. So if you take the second one, the water content at natural state is 25%. Find the liquidity index and soil consistency. So liquidity index is equal to W minus WP divided by IP. W means natural water content 20 minus WP 25 by plus index 10 into 100 equal to negative value. If it is negative value, you need to report it as a 0. Don't put negative value. So while reporting, we should represent the value in 0, not in negative values. So consistency is index is equal to liquid limit minus water content divided by plasticity index. Liquid limit 25 minus water content 20 divided by 10 into 100. So we will get the consistency index. So with this, all index properties of soil is completed. In next class, I am going to explain how soil is classified as per Indian soil classification system. So if you have any clarifications, you can ask now. Chetan, Chetan,
Hello, sir.
recording Nikhil Sai కదా Nikhil Sai, Nikhil Sai,
Sir, చెప్పండి
రికార్డింగ్
సార్.
నీ దాంట్లోకి వస్తుంది. రికార్డింగ్ విల్ బి సేవ్డ్ ఇన్ LE110 నిఖిల్ సైన్ వస్తుంది. అది నాకు పంపించవు, అది నా మెయిల్కి.
ఓకే.